All right, so
grab a chair.
So in the BOF, that is a set of topics that it came from several people, and I think it would be nice if we could actually discuss about them. In theory, here we have kernel people and we have toolchain people to be able, so we should be able to reach to some decisions and to do something productive today. So some of the topics, additional topics are welcome. So if anyone, for the BPF, we have in the afternoon a dedicated BOF. So anything that is specifically related to BPF, maybe it's better to leave it for this afternoon. However, you know that the BTF stuff, the BTF linking on the kernel side, I moved it to this BOF because it also impacts other parts of the kernel that are not necessarily related to BPF, like phol, right? Yeah. So if anyone wants to propose another topic, now is the time. So we have 3 persons participating remotely via Zoom, which is Miguel Ojeda, who is the maintainer for the Rust for Linux project, which is the project to get to write part of the Linux kernel in Rust, which is already happening, and he wanted to bring up several topics related to one of them to Debian packaging. So I'm glad to see Doko here, and also, Alan McGuire is also remotely, and he would like to propose an alternative or a way of actually doing the function inlining in BTF, which seems to be like more elf-friendly than the one that was proposed, I think, in the BPF mailing list not long ago. And who else is remote? That's it. And that's it. Okay, so that's it. So, what should we do first? I mean, some of those topics are like big topics. Like, we could start with the
I think we should start with the remote people, since they've actually dialed in and made the effort. The rest of us can always talk in corridors and things afterwards, but they can't.
That's actually a good, yeah. Thank you, Nick. Okay, so are we supposed to hear the remote people? So I don't know. Like, I don't know, anyone, manifest yourself.
Hello.
Hello. Oh yeah, I can hear you, but it's, where's the volume here? If I switch this maximum volume, I'm gonna kill you. Yeah, okay. Okay, say hello, say something.
Hello, test.
Okay, it worked. All right, so who wants to go first? Miguel, you or Alan?
Either is fine.
Okay, Miguel, for example.
Okay.
All right. Okay, let me get to your Rust for Linux. Miguel, can you see the screen that we are sharing? Yeah, I think you can, right?
More or less. Let me see. It's a bit hard to read.
Okay, so basically here is the Linux kernel is buildable with both GCC and Clang. The GCC support is important in this sense because of all the many targets it supports and LLVM doesn't. The Rust written components have been already introduced in the kernel, so it's no longer an experiment in that sense. And those are the 2 proposed topics that you suggested. The first is the packaging Rust toolchains for the kernel in distributions. And the second one is the building the kernel in the compiler CI, in GCC CI. So, stage is yours.
Thank you. So, so the first topic, and I will try to be quick. So the first topic that is something that we have been discussing for a while. We have been talking about how to package a Rust-enabled kernel in Debian. And there has been a problem that was raised by Noisy Coil, Ben, and Bastian. We were discussing, the 4 of us, in an email thread a while ago about how to support the out-of-tree modules. So let me give maybe maybe a bit of context, but so the issue is really, and I can send you, Jose, if you look at your email, I can send you, maybe it's easier if we put a quick slide. 1 second, let me.
Yeah, I can access my email here.
It's just a single slide, but
do it while you're sharing.
Let me send it to you. So I send your email, an email to you, Jose. Yeah, so let me, meanwhile, Jose maybe is able to put that up. So the issue is, okay, so Debian compiles the kernel natively, right? They use, for every architecture, they compile the kernel natively, which means, for example, for the official package for Intel, for x86-64, it's built on a similar, or the same architecture, right? In a computer that is Intel as well. So the thing is, they support for many packages, they support also cross compilation, and in particular, while they build all the packages, the official packages, they all build them natively for several reasons that Ben was explaining to us in Cangrejos a few days ago, the Rust for Linux conference. So the issue is they also support out-of-tree modules, of course, and out-of-tree modules, they support, Debian supports both compiling them natively, of course, and also cross-compiling them, right? So maybe you can put the slide now, Jose. Do you have it, the PDF that I send you? It's easier to follow, otherwise we may get all confused.
Did you send it right now?
Yeah.
Okay, let's see if I can have it.
Otherwise, it's not a problem. It's just it was something to.
No, it's fine. Yeah, I think I got you. No. No, I did not get it. Anyway, I think I can, from what I understood at Cangrejos, maybe I think I can sort of summarize. Just please correct me if I am wrong. So basically, in Debian, they build modules, kernel modules, both natively, and they also cross-build them, right?
So they support cross-building, but the official packages, they always do native builds. So I confirmed that. A couple of people told me, if so there is somebody from Debian, they can also maybe confirm and correct me if I'm wrong. But what I got is from them is they build all the official packages, like the kernel packages and the modules, natively. So for every architecture, they use a computer of that architecture, right? Now, the problem comes with out-of-tree modules. Because out-of-tree modules, Debian supports both native compilation and cross-compile out-of-tree modules, right? So if you are doing a native build, everything works, everything is fine, right? But if you are cross-compiling the out-of-tree module, then, well, first of all, I want to clarify, because I also asked the kernel side, and from what I got from Greg, the kernel only supports a single pair host target, or rather build host, right? So if you use a toolchain for building the kernel, you are supposed to use the exact same toolchain, the same binaries, to build all your out-of-tree modules, right? So Debian is supporting that out-of-tree cross-compile build for out-of-tree modules, but that, as far as I got, is not really supported by the kernel. It works, of course, but it's not supported, right? That's for C. That's for the C side, right? I didn't put any Rust into it yet. So for C, the Debian supports that cross-compile out-of-tree modules, but as far as I understand, it's not really supported by the kernel. I mean, it works, of course, it's supposed to work, but it's not officially like supported. It's not meant to. If you really want to use out-of-tree modules, you are supposed to use the exact same binaries of your compiler to do it. So if you did a native build, you are supposed to use the same toolchain. And if you are using GCC, that means, of course, using the same. You are still doing a native build, right? Now for Rust, what happens with Rust? The thing with Rust is the Rust compiler, the Rust C1, I mean, essentially generates some files, are meta files and set object files that the compiler uses, right, itself. So those files depend on details of the compiler itself, right? So therefore, those files, which are like generated headers to give a simplified, it's like data structure of the compiler dumped into the disk, right? So those files depend on the compiler that generated them. And therefore, if Debian natively builds the compiler, the kernel, right, the compiler, the Rust compiler, is generating some files that depend on that binary, on that Rust compiler, right? So therefore, when a user in Debian wants to build an out-of-tree module written in Rust, then the compiler will be a different one. It's a different binary, it's a different architecture, and the compiler will reject loading those files, right? It will reject loading those files. So that's essentially the issue. Now, the first question I want to ask is, first of all, how often, because out of three modules, of course, are like a second order thing, right, in the kernel. So of course they're important, but they are second order thing. Is it really important for, I guess, everybody or even Debian users, it's important to have support for out of three modules, cross-compiled ones? Like, of course, out of three modules work, and in Rust they work. We have support in the kernel to build those. But is it important that we support those out of three cross-compiled kernel modules? That would be the first question for the room.
So,
yeah, it
it's on. Okay. So is it also important if you do the native, if you use native compilation for the kernel and for the out of three module, that you are using exactly the same compiler binary to build the out of three module, or is this only when you mix cross compilation and not non-cross compilation?
I could barely hear. Sorry. Maybe Jose, can you repeat, or is barely?
Yeah, I mean, Richie was asking if this issue it only happens when you mix the native and cross, even if it is the same version of the Rust compiler, when you do that with the native and with the cross, or if it also happens that it doesn't happen with native, right? That it only happens in cross.
So I'm supposed to answer that or him? Sorry, I can barely hear him, so I don't know if he's saying something.
Yeah.
So yeah, the question is, does it also happen when you are doing native compilation? So if I have a slightly different compiler binary, will it also break the out of three kernel module build or not?
That if it also happens when you are native, if you have a slightly different version of the compiler, I think it will fail, right? Because they have a check in place.
For C and GCC, it works until you plug it.
Yeah, but the Rust compiler, they have those checks, right, Miguel?
Yeah, so the Rust compiler currently has some checks that essentially will not allow to load files from another compiler. Even if it is the same version, the same source code of the compiler, it will not allow to load those files. So you cannot use, essentially you cannot mix a native build and a cross build.
But natively, if you use two slightly different versions of the compiler,
it will also complain. Yeah. You have to use the same Rust version. Yes, it's everything the same. So it will, because essentially currently the R-meta files, which are the ones that really give the most trouble, I think. Also the server-object files that it uses as compiler plugins, but the R-meta files are essentially currently, as far as I understand, some data structure of the compiler dumped into disk, essentially, or similar to that. So, yeah.
Okay, Doko wants to say something.
How does a kernel tell that the compiler is different? So what's the criterion for the kernel to tell it's the same compiler?
How can it tell the compiler?
How can the kernel tell that the compiler is different?
Not the kernel.
It is the compiler when it links that.
There are, at least there were, I haven't looked at this for a little while, two mechanisms. One, a strict mode where it actually embeds in an ELF section details of the compiler version and the architecture and all of that stuff and makes it match. There is a mechanism called mod versions, which attempts to make those checks much looser and try to detect if structure formats have changed, if symbols have changed. Perhaps there's no version of mod versions for Rust, and perhaps that is what's needed here.
Have you tried that, Miguel? John is mentioning that there is a strict mode and that there is a mod version mode, which is more lax. It's not that strict.
Yeah, so it's not. So this problem is not really. I think it's a different because the mod version, etc., is taking the symbols, right, and so on and so forth for the modules. It's not really that. It's literally that the Rust compiler disallows using completely any generated file from another version or another Rust compiler. So it's really, for example, when you know in C you have headers, right? To give some context, in C you have some headers which are there, right? We manually write them most of the time. But in Rust, we load, the Rust compiler generates the equivalent of C headers, let's say, to simplify the picture, right? It generates some the equivalent of C headers, and then uses those files itself. So the compiler generates some files that then the compiler will use in different translation units, right? So the problem is that the Rust compiler does not allow to generate those files with one version or one architecture and then mix them with another binary, with the same compiler in another architecture, in another. So you cannot mix essentially Rust compilers. It has to be the same binary, right, to compile everything.
That's your sorry.
Yeah, fix the compiler.
Fix the compiler, yeah, but okay.
So one thing to that, we talked with, we discussed this on Cangrejos, and Tyler from the Rust language team said, well, it could be eventually be done, like it could be relaxed, so that because the compiler will need to track essentially everything and guarantee that the algorithms and everything is exactly deterministic, etc., so that everything works, right? Now, so that's fine. They could fix that, but as far as understood. Well, first, the kernel doesn't really support that to begin with. So even if it's supposed to work, and we make the Rust C compiler work with that, the kernel doesn't support to mix the binaries anyhow, right? So yes, it may be useful for what we do, but I think the only real solution from what I get that would work today, that would work for Rust C, so it would work with the current Rust C, and that it would be supported officially by the kernel, as far as I understood, Greg. The requirement from Greg that we always use the same pair build host. So what it would work is that Debian, if they want to provide the out-of-tree cross-compilation of out-of-tree modules, for example, from architecture X to architecture Y, what it would work is that Debian provides packages with that done. So they cross-compile the kernel, right? They cross-compile the kernel themselves. They provide the packages of that cross-compiled kernel, and then the users will use the same toolchain and everything to build the cross-compile out-of-tree modules. Of course, that means a lot of resources because you need to essentially give your users cross-compile kernels, not just the native one, but you also have to provide cross-compile kernels that would be essentially equivalent. But that would be supported by the kernel, and it would be supported by Rust.
Okay. So Miguel, so you have a workaround that you can suggest to the Debian people.
That's yes, as a workaround, but of course, I don't know if there is a Debian person in the room. I mean, that would work.
Yeah. Okay. So what?
Not current person. So.
Okay. So because we have to move on.
Yeah.
So if you have a suggestion for a workaround until they fix that compiler, then
okay, that's one solution. Yes, I don't know if they would like to do that because it's a lot of resources, but that would be one solution. And the other, there's another workaround, but that's a complete hack. Noisy Coil from the Debian Bananas team, I think it's called, tried.
Yeah, the Bananas.
Essentially, yeah. So they essentially tried to, they took the native build, they copied it into the out-of-tree machine, the other architecture, right? And then that architecture, they did a twin build, which essentially they compile the kernel, they cross-compile the kernel in another folder, right, for example.
Yeah.
And then they took the files generated by that Rust compiler, they took them and copied them replace the files of the native build with those. And therefore, now you can do an actual cross-compile and it would work, right? Because the files will be generated by the same compiler. So that works, but it's a hack because essentially you are mixing the files from one build of another with another.
Okay.
Could you write it out?
Yeah, we need. If you have suggestions, then maybe we can get you in touch with the right people at Debian. Yeah. I don't know who are the maintainers of the Debian. Well, you had Ben, right, back in Kernel.
Yeah, Ben and Noisy Coil. Yeah, I am in touch with them. I wanted to essentially, raise if there was a Debian maintainer, I think in the room, right? There was you said Poco or that I wanted to raise the problem. But I mean, really, the problem only happens if we think Rust enable cross-compile out-of-tree modules are important. Yeah. Those three conditions need to happen, right? It needs to be cross-compile, it needs to be out-of-tree, and it needs to be Rust enabled. So if that's important, those are the workarounds. Yeah.
All right. So we figure it out. Now the second point. Oh, by the way, is any of this will be a problem with GCC Rust?
So that's the other thing. Well, it depends, I guess, on how GCC Rust. If they support they are more flexible and they support, mixing the files or whatever files. Because I don't know even if they generate currently are metas or anything. Maybe they generate completely different files. I would imagine they generate completely different files.
So Pierre, we have here Pierre and Mark. Do you see any problem that we will have any similar issue like this, like with GCC Rust? Well, can you mix object build with different versions of GCC Rust and link them?
I don't know.
It's far too early to say.
Okay, so maybe that's something that you want to keep in mind, when you reach that stage. Okay, so let's move on. The other thing is.
I didn't hear you the last.
No, I asked that the GCC Rust people here just basically to keep this in mind when they reach the stage that they can link objects and. Okay.
That could be an advantage of GCC Rust compiler.
Yeah. Okay. So the second point is, as far as I understand, because we have to speed this up a little bit. Yeah. You was interested in having. Maybe the GCC test suite actually trying to build when they can start being able to build the Rust for Linux parts with GCC Rust to have some test suite in the compiler that builds kernels.
Yeah. So I lost your audio, but okay, I will reply. So I hope I am not speaking over anybody because I don't hear now. So to give on some, this one is quicker, so I will not take a lot of time. So essentially, the kernel currently we have in the Rust CI, so the upstream Rust CI, the Rust compiler one, the Rust language one. In the CI, every PR, every pull request that is made there has to pass before the merge, has to pass the CI. Okay, and that CI now compiles the kernel since a while, since like 1 year or something like that, right? So we are building the kernel there, and it was important we did it because I wanted to do that, and I requested that because we were using unstable features, what they call unstable features, blah blah blah, etc. The point is, the summary is they are building the kernel there. I think it was great. It has been a great success, I think, on building the kernel there, like the Rust part only. And I talked to, because that worked, right? And I think it was a good idea, not just for Rust. I talked to Aaron Baldman, the Clang maintainer, and I suggested, hey, can we do that in Clang? And then I talked also to Jose, and I said, hey, Jose, can we do that in GCC, maybe, right? I think even without Rust in the picture, I think it would be a good idea to build the kernel directly in the compilers. I mean, the Rust compiler is doing it. I think we can do it also on the C ones. That would be great for different reasons. But on the Rust topic, eventually, I would guess we want to do the same in GCC Rust, right, when it's closer to ready. In fact, we could maybe start the thing now. I talked to Arthur and Pierre a month or something ago, and talked about starting to build the kernel in a separate CI or whatever. But the point here is, can we start maybe preparing building the kernel on GCC, and then eventually when GCC Rust is ready, then we will have it there and we can enable building the kernel in the GCC CI. So I wanted to ask how wild the idea is, how feasible it is, etc., etc. We talked the other day in Cangrejos, Jose and I, about this, and with others as well.
Okay, so on the BPF backend, we are now, as part of a GSOC project, we are adding a test suite that actually uses a script that builds a kernel, basically, as part of the process. So would it be any objection to eventually have a Rust test suite in GCC that will build kernel?
They're having problems with audio, so we're trying to sort that out.
They are not hearing us.
They're not hearing you at the moment, yeah.
Okay, let's move on. Let's move on. Okay, thank you, Miguel.
The room is muted. I don't hear anything.
Yeah, can you hear me now?
Now I hear you now, yeah.
Okay, well, thank you. We have taken good note of everything, and we will maybe over this cauldron to discuss about those things and hopefully get back to you with some solution. Sounds good?
Thank you.
Well, thanks to you. All right. So, should we do what? S-frame maybe?
Is there someone else on remote that wants?
Yeah, well, Alan, are you there?
Yeah, I'm here. Can you hear me?
Yes. Okay. How can Alan, if Alan shares something in the screen in Zoom, can we see it here?
You're already in Zoom, right, on your computer?
No, but can we see it here if he shares something in Zoom?
Do you have the Zoom session on your computer? Your computer is the one who's connected.
Oh man. Okay. Yeah. Okay.
We can.
Okay. Well. Okay. Okay, I'm gonna switch to my graphical environment. I have no idea what is there. All right? Okay, you know what? I'm gonna disconnect and do it first. It was not that bad. It was bad though, but not that bad. Okay, Zoom. Okay, sorry, now I have to go back here, right? Okay, it doesn't work. Faust, can you bring your computer here so we can plug it there? Yeah. You are hosting the Zoom, right? So it will be perfect. Yeah. Sorry, it's our first time doing this.
What could go wrong?
Nothing, of course. More than once or twice a minute.
Inception.
Okay, is that visible to you guys?
Yes.
Good stuff. Will I start?
Yes.
Yeah, sorry, I try not to make it too presentation-y, but it probably just works a little bit better when I'm not there. So we've been discussing for a couple of years now about representing inline information compactly and simply in BTF to allow you to trace, because if you have K probes, you can kind of trace pretty much any instruction in the kernel. But what we're lacking is the information about things like inline sites, where they are and what their parameters are. So what we need to do is find a way to compactly provide information about those site addresses and how to get at the argument locations. Like, are they in a register? Are they a constant value? Or, can they be found via an offset from the frame pointer or something like that? Another goal as well is we don't want to pollute the existing BTF information with this information, because obviously the BTF will grow significantly if we dump in all that information about inline sites, because on a kernel I built recently, there's sort of 400,000 of these, so that there's quite a lot. So the aim here is, we've kind of talked about this a little bit. Thierry in Meta has had a prototype. I've been playing around with a kind of a simplified mechanism to represent inline, so I'll just quickly describe that here and maybe we can discuss. I've got an RFC series which is pretty much ready to go, so I'll send that out later, so we have something as a reference that works. The challenge is kind of getting this to work across the whole tool chain. So what I'm suggesting is, I think in Thierry's prototype he had a new section. So if you're familiar with BTF, it has a section for strings, for names of functions and arguments, all that kind of stuff, and has a section for types, all the different structs and integers and all that kind of stuff. So it has those two existing sections, and then it has, the type section has IDs, which are basically the offset within that type section, and they describe the various types that we have. So I think the original suggestion was to have a kind of location section, which basically took the dwarf location information from inline sites and kind of put that in a separate section. So what I'm suggesting is, actually we use just normal kinds, like we have type kinds we have for actual types to represent locations. So the idea is basically that we kind of mimic what we do for functions. So we have a location parameter, which is basically a representation of how you find location information at an inline site, and a location prototype, which is a series of those parameters. So basically your location prototype says, at this particular inline site, here's where you get all of the what would be function parameters, but it got inline. Now, obviously, in some cases, there isn't information, we can't recover a parameter because there isn't one, or the location information is sufficiently complex that we don't want to deal with it. So in case like that, we just use a 0 for, to represent that we don't actually have a parameter in that case. And then finally, we have a section, which has a set of representations for each of those locations. And the idea of that section is it kind of pulls together the name of the inline site, the function prototype associated with that inline site, so what the function would look like if it hadn't been inlined, and all the types associated, and then the location prototype as well, which is where you map from that function prototype with all the types to where the actual data is stored in registers or what have you. And then finally you have an offset, which tells you where the address is base, relative to the kernel base. So the idea is we have one of them. What we're trying to do, the representation really focuses on making the location parameters and prototypes as kind of neutral as possible, not containing information about the specific site, because BTF allows us to deduplicate, which is basically means take information about coins that are the same and kind of boil them all down to one, so we don't have a huge amount of overlapping information. Because you can imagine an awful lot of location sites, inline sites, are going to have a register number, the same register number. So if we can have all the location parameters referring to that same register number, that's going to save a lot of space. And in the same way with the location parameters, we'll have a lot where they'll have, okay, this is a function with no arguments, so it doesn't have any locations, or it's got one and it's a register. So the deduplication process will actually save us an awful lot of space. So it's sort of like this representation isn't obviously as compact as kind of squashing all the location information into a section on its own, but we're sort of taking one step backwards to take two steps forwards, in the sense that deduplication will hopefully save us. And then, so the location sections here, the idea with them is basically we've got one for each inline site. So like I was saying, for a kernel with 400,000 inline sites, there's going to be 400,000 entries in the location section. So these are a little bit like, so the location parameter is a little bit like just a normal type. The location prototype is a bit like a function prototype, but with a set of location parameters. And then the location section is for all the various sites that we have in the kernel. There's some specifics there. I don't know if we need to dive into that, but basically it's just a way of telling you where you get your location. In some cases it can be a register. In some cases it can be a constant value. We use the BTF kind flag to separate between the two. And then we have a kind of a union there where the register number, any flags associated with that register, like is it a dereference, and then an offset are specified. Otherwise, then it's a 64-bit value. And then we can actually use the type from the function prototype to actually know what it really is in terms of the type. So in some cases, we might need multiple of those parameters, though, to represent a specific function argument. So one of the things we came across when we were using BTF in the kernel is there was some cases where we'd have a struct which was 128 bits and it was passed by value via two registers. So the idea is in some cases you'll have two location parameters to represent a function parameter, if that makes sense. So there's a way to kind of handle that here. So the aim is not to handle literally every location, because some of them are going to be quite complex, but it's to sort of cover the vast majority. And then the location prototype, that's quite simple. It's just a set of location parameters which are used at a particular location site, and 0 is used to specify we can't or don't have any location information. And then finally, the location section is, as I said, that's going to be the collection of all of the location sites. And since BTF uses a concept of a virtual length, VLEN, in the type, or value length, sorry. So because the maximum of them is 65,535, because it's only a 16-bit number, we have to have multiple of those location sections to cover like the 400,000 odd inlines in the kernel. So each of these is a site, so it's got a name, it's got a function prototype and a location prototype and an offset for the address as well. So to give a sense of what the numbers are for this, for about 400,000 inline sites on the kernel I'm building on, 65% have location information for all the parameters using this scheme. 5% are functions which don't have any parameters anyway, so we don't need to represent location information other than the offset and the name and the function prototype. About 12% have no location information, but they should have had in an ideal world, but we couldn't recover that information, or the locations were too complex. So, and then finally, about 70% of location information for one or more, but not all of their parameters. So you can see we cover a fair bit with this scheme, even though it's quite simple, and it's intended to be simple, but to try and gather as much information as possible. So that's the trade-off. And when we use deduplication in this environment, sorry, someone say something? No, okay. So location parameters are heavily deduplicated, so we end up with only about 12,000 for those 440,000 sites. And similarly for location prototypes, you end up with about 37,000. So the long pole here is obviously the site-specific stuff. So there's about 400 and whatever thousand of them at 16 bytes each. So that's 6.5 megabytes. So the whole thing totals about 9 megabytes. Now my aim, and of course in hindsight, it's always convenient when your goal actually meets what your initial aim was. But the idea was we want to have a representation which is a similar order of magnitude as the existing BTF size is today. So today, usually for a kernel, the VM Linux BTF is around 6.5 megabytes. That's what I usually see. So it's in the ballpark. Obviously, it's a bit bigger. But one concern is we want to separate the information, obviously. So we need to have a separate, like a VM Linux.extra, which is loaded by a module. So I'll either have a separate directory or have a separate file where the BTF is made available to user space for tracing. Having a separate directory might make sense for backwards compatibility because a lot of tools will look in syskernel BTF and assume everything that's not called VM Linux is a module. And then in terms of generating info, I've got a prototype PA can do that. It can iterate over multiple inline sites. If you specify a new feature inline, it will generate all that information. And you can specify an optional suffix, which will actually create a .btf extra section at the same time as generating the main BTF. And then it will deduplicate the main BTF, and then you'll generate your extra section on top of that. So the idea would be we'd sort of deploy this with a VM Linux extra module, which is optionally built. So the idea is that VM Linux doesn't get massive with 9 megabytes of inline information. It actually stays small, and then the extra can provide the BTF extra location information, and you can use tools then to trace at those locations. So the idea would be you'd use something like kprobe multi-attachment. We have to use kprobe since we don't have fentry sites within bodies of functions. And a single line can obviously be in a lot of different sites. So you'd have some kind of section name, which would like kernel locations. And you could populate then a BPF map, which would give site-specific info. So that's roughly the idea. But the idea is I'm going to send out a prototype soon.
Can you hear me?
Steven,
Where?
here, because
Where?
this is getting the sound for soon. I think
Okay.
that's good.
Can you hear me?
Yeah, I can hear you.
Okay, so this is Steve Rostedt. Actually, because listening to this, one of the biggest complaints I've always had about the function tracer is the fact that you can't trace inlines. Now, here's a question from these guys. If we were to do something like this, would you be possible also to inject like no-ops where the inline would have been placed? So if we were able to go back, we could actually patch those areas for kprobes or whatnot to be able to. So kprobe's a little more complex to patch something. It either puts a breakpoint in and it has to emulate the code, or we could patch it. So patching's a lot quicker, easier to do. So if we were to do something like this, if like the compiler would just inject just a no-op that's big enough to put a jump or a call or something.
You can do that. You should be able to do that, but it will be quite a bit of performance overhead.
It would actually obviously be an option. Oops, yeah. So it would actually require an option to that. I mean, would that be also something that would be useful? I mean, from
but there's no obvious reason why the compiler could do that.
Yeah, because if we're going to be implementing this, maybe have, because this means we want. Oops. Are we off?
Yeah,
Are we off?
Zoom's dead. The
So,
recording's not.
what about the Zoom? Our
we have to rest. Apparently, someone did not buy the premium account.
Should we wait to pause until so they, because right now we lost our remote.
I think we should probably move on anyway.
Yeah. Okay. So just something we'll just add. I should say, just keep me in the loop somehow in this conversation if there's emails going on.
Okay.
All right. So.
So these are good for the recording.
Yeah. So I'm seconding Steven's request for GCC to do something there. So what we thought about doing the experiment on the LVM side, since it's easier for us to hack a LVM. What? Well, so the idea that we will add some sort of, the performance overhead, like understood, but we're thinking to add sort of like fake inline ASM into beginning of every function, not of every function, but like with some heuristic. If it's like inlined everywhere, like a spin lock will be bad. But certain functions that get inlined into small number of locations, they're not like trivial. Just adding this volatile ASM that captures the arguments will be and behave like USDT. It will be just like extra knob5 in the places where the compiler would inline this knob5 with extra annotations USDT style that will go to this like stub style like section, and that would help a lot. And ideally there will be like no additional overhead, because yeah, if there is overhead, even if it's at whatever extra 5% slower for the kernel, like we're not going to use it in production. But so this got to be like as close to zero as possible, and it seems possible to do with good heuristics where to place this extra volatile ASM.
So Alexei, I just wanted to confirm. So basically what you're saying is have metadata that tells us where like the parameters for the inline function would be. And that, I mean, you wouldn't be.
Yeah, the metadata will be like similar to what both like GC and LLVM do when they process the USDT. They just record, well, currently as a string where all of the arguments are, and that works well enough. It's not pretty, but the tooling understands all of this.
And if it was like a parameter was optimized out, we'd have to have information that the parameter was optimized out.
It won't be optimized out. That's the thing, because like GCC, because it's volatile ASM, both GCC and LLVM, let's say the constant is being passed. Even the constant is being passed and it's used within the function body as a constant, the compiler will still put that constant in the register and will say that's in the register. So it's like extra necessary code emitted, but from a tracing point of view, it helps a lot because the arguments will not be lost.
Well, I think an argument could actually be completely optimized out, because let's say, for example, the inline function had an if statement or something, and if it got inlined, it knows that this if statement is not being passed, and the argument was only used. So that basically, if a block of the if statement was optimized out, and the argument was used in that if statement, in theory, I believe the compiler could optimize. So
the body of the function will be optimized. That's what I'm saying. That
you're saying to prevent that from happening, but that would have an overhead.
No, that's not what I'm saying. The body of the function will be optimized as whatever was constant propagation, etc. Like everything, all the optimization the compiler will do is just that the function entry at the function entry. Whoever is passing whatever arguments will be preserved. That part will be seen. So when we're tracing like all kind of functions, we want to see like who was calling this function with what, and that information still be there. Even if compiler like did cloning with whatever, constant propagation, etc.
So basically, like I said, if it was using a parameter, like say a function, like the actual function gets called with a parameter, but that parameter is never used because the inline it was passed to the inline function, say, and the inline function got optimized out for some reason. That could just happen. But that parameter, since it was passed, it would still be exist somewhere, I guess.
That's like, okay, here's like a concrete example. Let's say you have a function foo with two arguments, A and B. And somewhere it's like called in different places through the kernel. And in some places it's called, let's say, like with some actual variables. These variables will be in like two registers annotated, and in other places it's called with like some variable and a constant. And constant gets propagated down in that inlined call site, will optimized out, but the compiler, because it's volatile ASM and in front of it, will still emit move of that constant into like second register, XDI, whatever, EDI, RDI, that will be like based on like x86 like calling convention. So it will be like a necessary move, but like the rest of the function body will still be properly optimized. So there is an overhead, but it will be like so tiny that should be acceptable.
So wait, you're saying to actually still, even though it's not used, to still do the move into the parameter of the function parameter?
Yes, only to preserve the arguments.
I think that could, well, I mean, do we even need that? So
for tracing would do.
No, I'm saying is if it's still, like I said, if the metadata could say where, because the data could possibly still exist, even though it got optimized out, it existed somewhere else. Well, you're saying is
you're asking for an improvement. What Alexei is saying is, given the compiler as it currently exists today, this will work. And you're saying, well, wait a minute, we don't have to have those extra moves, and that's true, but that's something that needs to be modified. Well, it does slow it down a little bit. Alexei's saying for the use cases he has in mind, that's okay. You're saying there's a way to do it without slowing down.
Definitely, that would be way better. I'm asking, I think, for like bare minimum that compilers can do without major surgery to the compilers. They already understand what's like volatile SMS, how to pass all the arguments, how to preserve it, not optimizing out these arguments, etc.
We just have to measure how much performance overhead this
minor
gives.
extension.
Yeah. In other words,
I think, well, one important thing with the inline functions is most of them are not continuous in the emitted code. So even if we emitting a knob at the start of every inline function is not really hard. We could insert there a built-in internal function and turn it into a knob. But the problem is that the knob can travel very far from the rest of the inline function. It can be the inline function can be split into multiple assembly statements, which will be far from there or optimized outcome.
That's true. That's true. But there's a lot of use cases where that's okay. Yeah. So, for example, if we just wanted to have something that counted did a histogram of how often the function was called, what its parameters were, then we could do that even though, as you say, the function gets kind of smeared out with a bunch of other functions. Now, if we wanted a single step, you're right, that would be a pain. Does that address things, or am I missing a subtlety where what I just said wouldn't work?
No, I mean, you need the knobs to not be dispersed.
No, I think we only care about the entry, which means that we can't do we can't do any tracing of exit from the inlines. It's only entries that we care about.
Well, you could trace the exit as well, but
No.
the entry and the exit
it doesn't make sense because, as you said, the inline could be spread throughout, so it could be intermingled with the actual function.
A single assembler statement can actually be Honza had a test case where it's 3 different inline functions completely unrelated.
Well, I said, if the inline function had a return value, maybe we want to do something like that.
If you wanted also the arguments, maybe you are basically asking for something like asking the compiler to emit the system tab markings of all the parameters at the start of the function. That's also doable, but we would need to. Right now, system tab works as a header, which can be changed from time to time, and we would need to hard code it in the compiler.
In quite many cases, you cannot.
Microphone.
In quite many cases, you cannot reconstruct the parameters of an inline function at all. Like what the statistics, slide back, whatever, showed, there's about 30% of function calls where you cannot. Where whatever was used cannot, at least, right? It might be possible in theory to do it some of the time. 30% is quite a lot, but 20 I would certainly believe, and the same way you could reconstruct the return value for the return. But when would it ever be useful? Even when something is called, right? When a function is called. The whole point of inlining is that it is optimized heuristically, globally, whatever the word for it is. So it is intermingled with all kinds of stuff. So who cares when it might have started, and for source code it started there, right? The function was called, but who cares? That's not what the machine is doing. So,
The one thing I would say that I would love to have is like when the compiler decides to inline something that wasn't marked as inline, or just starts inlining stuff. It does that quite a bit, and because I've had people, and it's even more confusing when it inlines sometimes, but not always.
Right.
And that's where when someone enables function tracing and they come to me and says function tracer is broken, I've seen it, I put a print statement in and it prints the statement, but it never is traced. And then when we decompiled it looked at the assembly code, we noticed that it inlined in that one instance that they were complaining about. So that's where you say it's not working when it actually was working. It's just we don't trace inline functions.
Right. So there is one. I want to ask you, actually both of you, a question. Suppose we had a pair of functions were inlined, and you called function foo and function bar in that order. And so what the thing is, we put a little thing in, like we do for K-probes. I'm sorry, I'm not using the wrong one. System tab, thank you. And the thing is, what I think you're saying is those might come out of order. It might, we called foo, we called bar. The system tap for bar might come before foo. I mean, that could be okay, but we want to know about it.
Yeah. So I think it is target specific, and this will be for power what I'm talking about. But is standard stuff to put an obslet at the start of every function. So that might be generic even, but that is very useful for the kernel. And the overhead isn't actually that big to put it at every function, because there aren't so many function calls. Functions tend to do a lot of work except call other functions. Yeah.
Mike, over here.
I think also a question is if it's something useful for other projects than the kernel, or only for the kernel. If it would be useful only for the kernel, then maybe the best idea would be to put a plugin callback in the inliner, and then you could have a kernel plugin which uses this hook.
Well, I know Linus hates
plugins. At that
plugins.
point, you can insert anything you want there.
Linus hates plugins, so that's one thing. But
so if there will be any other tracing infrastructure that will be interested in doing the same that you want to do.
The thing is, what we found out, like with everything else, the ASM go-tos, F entries and stuff, they slowly leak into being used in user space. Yes, right now, I mean, I'm a kernel developer. I care about you. I don't do tracing of user space as much. So I may not see the use case, but once these things get available and people see them being used, then the user space says, oh, that's available. Let me start using that. They're not the ones that are usually sometimes asking for this. It's like the kernel's kind of like cutting edge, pushing stuff. Then user space says, oh, we could use this now. Just like I said, VASM go-to and the like F entry, that is now being used in user space. So it's like, build it, they will come, but we will use it.
Well, in the user space, you can more easily use dwarf to find out the first instruction in the inline function and where the parameters are and so on, without any changes, because it just works.
Like I said, there's people who, like I said, when they're doing production code, some things like this, or when because the kernel tries to be as optimal as possible, and a lot of times user space will then, that's like not all, like I said, it's sort of a niche thing. But there is going to be niche use. Like, I don't believe we're going to be the only ones doing this. Once we add it, I could see others start using it like they have with the other features that we've asked for. So, but again, with a plugin, I think Linus already said no on that, so I will, yeah.
Well, the thing with plugins is that you can play with it and see what works, and get the design right. And then if it's useful for everything, then it can be implemented in the compiler itself, because you have multiple users.
Well, I said how much overhead is something like this to be? Oh.
Well, I keep this plugin thing. It's like a recurrent theme here, right?
So I will say that if you can find some other userland user of this feature, then maybe we could consider adding it at some point. Yeah. All right. So we lost the Zoom session. So let's move on, unless anyone wants to say anything about it. Okay. So I really wanted to see, the S-frame stuff, because I think we have to coordinate here a binutils release, right? The kernel release. And now that Nick is here, we can actually, so who has the whole S-frame in the head that can explain?
I have slides.
Because it is binutils, glibc, and kernel, right? As far as I understand.
I mean,
oh well, maybe use that.
Here, I use this, and also,
I can say what I have in my mind right now. So basically, so far we have had one case where we saw this thing come into play that we needed. So we put in backtrace support in glibc, which came out in 242, and at the same time we were trying to fix things in binutils 245, and both of those were, so ideally this needed to be bootstrapped in the sense that you wanted binutils to come in first and then glibc follows. But this problem will manifest later too. Like we are planning to do SFrame v3, which comes out in, well, we want to do it in 246, right? And so glibc stack tracer will also need to be made aware of v3. So there is one, dependency right there, and the kernel, I think kernel 3 set of patches are in pipeline. So on the kernel stack tracer side, we need 3 different components, right? So 3 different sort of pieces together. So one is just the whole infrastructure around deferred stack traces. So that is already in, but the second pieces which need to come in are perf using the deferred stack tracing infrastructure, and then comes the SFrame stack tracer. So these 3 components, and the last one being SFrame, we do want to use SFrame v3. So in terms of coordinating the releases, that's now the open.
So in kernel, as I understand, there was the support for deferred unwinding, right?
Yeah, but it's not being used. It has no users.
But it was pulled.
Yeah, Linus pulled the deferred unwinding, and Peter Zilster's right now fixing it. So just to give you just an update, I had slides, but I don't know if you even need it. Just a summary. So way perf usually works is it triggers NMIs and to do the stack tracing. So when the NMI triggers, it does a kernel stack trace and then a user stack trace. Well, it just assumes that the user stack trace will be present in memory, because if it takes a fault, it can't actually process that fault because you're in NMI context. So it just will drop the SFrame or drop the stack trace at that moment. In most cases, it's not an issue because the stack usually is in memory for most of the time, and so you don't usually have to fault it in. Problem is, SFrames, all the data is stored in the ELF file or in the library that's in user space. So for the kernel to read the stack frame via, or do the stack trace via SFrames, it actually has to read user space, which is likely not present in memory, which means it has to be faulted in, pulled from disk, whatnot, to pull into memory. Can't do that from NMI. So we had to come up with a whole strategy on a way to defer the stack trace. Since when you're in the kernel, the user space stack trace doesn't change because you're in the kernel. We could defer it to when we go back to user space, which is in a faultable context, which means that when NMI comes in, we do the kernel stack, and we ask the user space, or we ask the deferred stack trace infrastructure to give us an identifier. We call it a cookie, because it's a unique identifier that represents that stack trace. So if you have a long system call and you have 5 kernel, or 5 times you do profiling, it'll do a kernel stack trace for each one, and then get this unique cookie. We'll get the same unique cookie each time, and then when it goes back to user space will trigger a way to say, okay, do the unwinding now, where it can now fault in the SFrames to do the stack trace, and then it sends it back to perf and says, here's the stack trace with the unique ID that you were using it, and then the perf user space will then take that user space stack trace and then append it to all the places on the kernel stack, so you get the full infrastructure. The deferred infrastructure has been made into the kernel. Right now we're working on the perf side of it, and also each architecture has to enable this. So even if we have perf doing it, that's why I think we say there's 3 different things. The infrastructure for doing the deferred, the user for ftrace, BPF, perf, to use it, and then we also need architectures. Each architecture has to individually say we support it, because it has some architecture specific things. What kind of things? Of what kind of things does architecture have to do? Well, for example, x86, it tells you what registers you're going to have to use to save. S390 is, where's S390? Are they? Yeah, there he is over there. They do something completely different. ARM does something different. Yes. But ARM 6, what gets, like, how do you read it? So basically, you have to, because every architecture has its own way of storing registers. And to get access to those registers, we have to do it. So there's...
And if you would just use the part debugging code, that's all in there already. But for some reason, kernel wants to use completely new debug format.
Wait, what you want to use? I mean, well, we have our own PT regs that we store the data for when an interrupt goes off, how we save the data for the instructions. That's how we get to the access. So each architecture, there's just 2 patches that are needed for x86 right now. S390 needs a lot more. But then we have the so that's just deferred unwinding, deferred stack trace. When we go back to user space, right now it could work for frame pointers, and S-frames is just one of the things. Right. Some I'll repeat that. Some architectures as S390 doesn't have. So they're some of the driving forces is to use the S-frame code for this as well. One thing that Arnaldo, I was just at Kernel Recipes just 2 days ago, and Arnaldo, who's the perf user space maintainer, showed me, I guess, x86 Intel specifically, I guess, has the hardware that actually saves. You could ask the hardware to do it, and he showed me up to like my machines only had 16 stacks, but you could do a full stack trace or stack unwinding, or not unwinding, a stack trace, stack walking via the hardware. I have to make sure I get the terminology correct here. In the user, by the way, kernels say stack unwinding, which means stack walking. So if you hear me say unwinding, I mean stack walking. I know they're 2 different things in the compiler, folks. Kernel folks, it's the same. So sorry about the terminology. So I guess the hardware, you could just say, give me, boom, and he showed it to me, and it works rather well. But if the stack is longer than that, then we may want still to use S-frames and whatnot to figure out more. And then, of course, there's one other thing is, if you're familiar with ORC, if you heard of ORC, ORC is a x86 way of doing something similar to S-frames, which is the table format to do stack walking within the kernel. It was needed for live kernel patching, because live kernel patching needs to make sure that whatever is being patched is not being used, so it stops the machine, checks every single currently running task to make sure it's not in the function that's being patched, and do that, it's got to do a stack walk of every single task reliably. And so ORC was created to be able to do this using the same methodology that S-frame uses to do that. But it's very specific to x86. ARM is currently, ARM64 wants to do the same thing. They want live kernel patching. So they first tried using ORC, but they said ORC was very much too specific to x86, and it was really hard to get converted. But now when they heard about S-frames, that now works on ARM64 and x86 and S390 and all that, they're right now using that. They want kind of use S-frames to make sure that inside the kernel, when they do stop machine, they can use S-frames to walk up the, do the stack walking of every single task, make sure it's not in the function being patched. And they don't have to worry about page faults, because in this case, the kernel S-frame sections will be present in memory always. Yes, so there's no faulting when we say in kernel S-frame, stack walking, that's present in memory always. So another reason why we want to make sure it keeps it compact. Yeah.
So
why don't you take this?
You mean it's always present already whenever you take an NMI, the kernel stuff will be there already?
Correct.
Okay, thanks.
Yeah, so we don't need to do any deferred stack walking.
And to just clear up a question from earlier, the reason why dwarf won't do for this is mostly as and leaf functions, because there are a lot of them. There are a lot of leaf functions in pure assembler in the kernel. For dwarf, they all needed manual annotation with dwarf CFI info, and that's never right. And if it needs to be reliable across the board, yes, but if it needs to be reliable across the board, you just hit one of those and all hell breaks loose. With S-frame, the assembler knows how to generate this stuff, and it nearly always gets it right, with the exception of a couple of edge cases that the kernel never uses hand assembler. So you've gone from something that basically doesn't work, except in the worst possible cases when you really need it, to something it always does.
When you say it always automatically gets it right, that's pure wishful thinking.
Okay, I hate to interrupt, but we really need to, I mean, because there is some releases to synchronize here, right? I mean, so, okay, what version of S-Frame will be supported by the kernel and when?
So that's really into.
I think we should do V3 for the kernel.
Okay.
So at least going from V2 to V3, we are planning to put, for example, support for text larger than 2 GIB. And if you support the glitch here is if you want to support in any stack tracer, both V2 and V3, it's going to be, it's not necessary. So we are just targeting support V3 everywhere, right? V3, yeah.
Will have to be there forever.
Yeah. So since we have the leverage now to sort of coordinate the releases, let's just do V3 right from the beginning, and then onwards we can maintain backward, compatibility in the sense if V4 comes, we still give enough, useful options in the assembler, in the linker, so you can still go compile V3 and V4. I'm not sure mixing objects, whatnot, but what to say is, basically what I'm trying to say is V3 onwards, we try to do the right thing in, binutils, that we don't break the previous versions. But as of today, I think the intent is that we just do V3. So, which comes to binutils, 246 is what I would ideally target. I think it's doable for 246, binutils 246. It's December.
No, January.
Okay.
The deadline for getting new features in will be December, but the release will be in January.
Yeah.
Okay, for December. Yeah.
At least for the feature set that I have in mind, which is the support for text larger than 2 GIB, marking outermost frames, and there was one more. So they are doable for December. There is a new patch set that has shown up for long arch, but I don't think we have to sort of. It's not contingent on. binutils 246 is not contingent of on how long arch goes from here. So that said, I think binutils 246 is what we are targeting for V3.
Okay, so on the kernel side then, first of all, we're not going to make this merge window. I think the merge window likely will open Sunday. Do you think? So this Sunday, that's what? Sunday, the 6.17 will be released, and that means the merge window for 6.18 kernel, Linux kernel 6.18 will be opening up for the 2 weeks, and that's probably going to be in what, December, you think it'll be released? Yeah, about sometime December it will probably be released, so we're not going to have 6.18 will not have SRAMs then, because if we're going to wait for doing this, probably easier just, okay, I was pushing fast before, but now let's slow down and get it right. So maybe 6.19, no, 6.19 would be about when? February-ish. So then we should, I want to make sure that the S-frame, if we're doing V3, I want it like the specification set in binutils. So probably aim for 6.19 or 6.19 or 6.20 or 7.0. So that probably is going to be more realistic. So February or whatever will probably be at the time.
Okay.
And just the last thing, what came to my mind is this. So I don't know how dependent we are on the release of S-frame support in LLVM. I think they were planning to do, I don't know the cadence actually for LLVM releases, but is it spring next year? That is what they were targeting. Well, that could be important for user space, like distro-wide enablement to have support in LLVM too.
I think we're going to need to see what Masquerade says about that, because he's the main LLD maintainer.
Right.
So if he's unhappy with the format,
yeah,
it may end up not in for that time frame.
Okay.
As for glibc, February. So yeah, that's fine. But yeah, I think at LLVM we need to sort of discuss and try to figure out what we're going to do there.
Yeah.
And then in glibc, there is an S-frame unwinder. What is Claudio? Ah, there you are. So the unwinder that we have in glibc now, it supports frame 2.5, right?
Version 2 errata 1, so 2.5.
And what is the plan for getting the version 3 supporting glibc? When is the next glibc release? In February?
No,
That will be 243. Sorry.
Yeah, I have to see that.
If I move up the BenuTools release, the 2.46. So if I move up the 2.46 release so that it comes out in, say, December rather than January, would that be helpful to glibc and the kernel folks for getting v3 support in?
So what was the question?
If I bring up the 2.46 BenuTools release so that it comes out in December rather than January, that gives you all of January and whatever February to do whatever v3 work.
Actually, I mean, it might be, we're not in a rush right now. I'm more worried about when the actual specification is finished. Another thing I just thought of when you mentioned libc, we're missing a huge component right now. That's the system call. We need glibc to be able to give a system call to the kernel to say, because glibc is the one that does all the dynamic, and the LD conf, whatever the dynamic linker code, it pulls in the S-frame sections. We need a system call. We're working on a system call to do this, and we want to make sure it's extensible to not only do libraries, but be able to do JITs and other things. So we need it accessible. So, and then once we make a system call, it's solid. It doesn't change. Once it's defined, we have to. So we're struggling right now to anyone that does JIT, like work here, like or Java or anything.
Not in 15 years.
Because we want to make sure we can make it extensible. And that's the hard part, is coming up with the system call to do that and getting it past Linus's approval and all that. So that alone could take several releases before we get that in. And it's the when it's built in the static function or static executable where the S-frame sections in the ELF file that's being executed, that's trivial. The kernel sees it. We already have code that works, sees the S-frame there, and then starts doing it. The dynamic linker right now, we have a PR control that's just for testing purposes, but that's not going to go upstream. And that's what we really need for libc and everything else. And that's where we're kind of struggling on how do we do this right without kicking ourselves 2-3 years later.
So if you really need it, why isn't it going upstream?
Wait, what's the...
You said, you said we really need it, and you also said it isn't going upstream. So
No, the PR control is not going upstream. That's a hack.
Right.
That's a hack.
That's a hack.
That's just that, because it's a system call that you just add a number to and it's there.
So you mean we need this functionality, but not this
the current, that's the PR control is just a system. It's like a ioctl for the kernel.
Right.
So we actually want a real system call,
Right.
which means giving a system call number and all that other stuff.
Yeah, and that does the actual work and does it correctly.
Right. The PR control is just for testing. We needed the functionality.
Right.
Yes, we need the functionality. We need the system call. Yeah.
It's a quick hack.
Yes.
Good.
Okay, so we are running out of time. So on the distro side, Sam, what would be the timing for Kernel to adopt v3?
So we're a rolling release, so it doesn't.
But you are keeping like.
Oh yeah. We follow. Yeah. So we haven't enabled S-frames like deployed binaries yet. Once v3 is sort of finalized, then we'll.
And it makes sense to wait for v3.
Yeah, and then we'll start rolling that out. But we can work with whatever. But we'll wait until v3 before deploying it.
Okay. Sorry. Yeah, there is no time for the topics. So actually, I wanted to. We have like 8 minutes. So I wanted, because Thomas was kind enough this year to go to kernel recipes. To go to kernel recipes to actually give a talk about the DCC And
can we plug this in?
Yeah.
All right, yeah, so I had the opportunity to present GCC and also the, or represent GCC at the Kernel Recipes Conference, which was just before Cauldron in Paris, organized by OSS Flow. Oh, yeah, you don't see anything.
I like that image, though.
That's from a number of years ago. That was labeled extreme programming, which was a hot thing back then.
What you had to do with your talk right now?
Nothing.
Each finger of the glove hits 2 keys, so you go twice as fast, right?
Yeah. All right, so that looks better. So, right, that was this, and we actually need this one here. Right. Okay. Yeah, so Jose had asked me to go there. I'm not really known for GCC kernel interfacing in GCC here, so yeah. But anyway, it was a good experience. So I work on the GPU offloading stuff, OpenACC, OpenMP, that kind of thing. So anyway, yeah. So this is just a short report. That was the title of the slide that we had there with the abstract. And that's what we covered just very briefly. History of GCC, some statistics on contributors. One interesting note, this has been mostly stable for more than 2 decades. So we are roughly around 600, 700 commits per month and roughly 100 of separate contributors per month. Stable for more than 2 decades. That's interesting. Of course, going...
Yes.
That's a separate discussion.
It's the next 2 decades.
Right. I'll get to that. Yeah, we had some discussion of the GCC structure in terms of source code, what is shared with other projects, of binary level, the drivers you invoke, how all that works with libraries and that get linked in and that stuff. A very, very, very high level overview of what GCC or a compiler does internally, some legal aspects of GCC, that DCO is now possible instead of FSF copyright assignment. Briefly covered GCC steering committee, and then moved to the community of GCC, what is in the maintainers file basically, external community, the distributions, other downstreams, the contribution process, just 5 easy steps, well, yeah, in theory. Project infrastructure, sourceware, primarily external infrastructure, for example, the CI testing that companies provide and feedback into patchwork, for example. The GNU Tools Cauldron, we're here. FOSDEM, GCC Dev Room, Google Sum of Code participation, which we'll have a BOF later today, I think. And then very short updates on GCC Rust and GCC BPF. So we had some discussion right after the presentation, and then of course more in the hallway track. We had a show of hands how many people use exclusively LLVM Clang to build the Linux kernel, which was just a handful. Everyone else uses GCC to some very varying degree. So it's still very much relevant. Right, and then this concern about the GCC and other GNU toolchain developers aging into retirement. But we are getting new contributors who just show up on mailing lists because they need, well, there was one guy, Alejandro Colomar, who is interested in adding diagnostics for stuff that in C++ should have diagnostics. So that happens, and of course the toolchain companies bring in new people, and people appreciate the outreach that we're doing, as mentioned here. Right, so this issue has been resolved. If there is CI testing of GCC BPF stuff, I guess that was answered offline by Indu. One person mentioned that he switched from GCC to LLVM Clang because having to routinely build the kernel for many architectures and doesn't want to install all the tons of gigabytes of GCC toolchains.
I have a project for that, just for that, where you can build anything. It's called build all, right? And
there's a reason for it. It builds utils for any architecture. It builds the GCC for any architecture, and then it builds a kernel for that architecture. And that's very useful for testing anything, right? But it has worked for over 20 years, maybe 30 years already. Yeah, it still works.
If you build every target GCC supports, you get about 5 gigabytes, and I don't believe no one have 4 or 5 gigabytes.
These are just some individual remarks that I collected here, yes. But indeed, it's
easier than when we have one driver and
there are ways, yes. And I know Joseph has written, Joseph Myers, such a long email what needs to change in GCC, so that something like this, what Clang has, would be possible. But yeah, not going into the details here. That's a very other thing. The no libc was had a presentation at the kernel recipes, which is a kind of, I understand, a wrapper around Linux system calls, so that you can have a minimal libc-like interface for user space code, and of course has some very limited printf implementation and stuff like that. They need, depending on what the compiler does, libgcc for modulo and division routines and that stuff.
How can you ever build a compiler without libgcc? The compiler is not supposed to work without libgcc.
In many cases, you don't need it.
Depends on what we use.
Yeah.
Maybe I can address that.
Sure.
So I should be very clear, nolibc is extremely subsetted and extremely special purpose. It's used mostly for people who are, so I don't know of anybody that is quite crazy enough yet to try to build a compiler on nolibc.
No C library, I can understand. That's exactly what I do for building the kernel thingy. But no libgcc. Libgcc is an implicit part of the of GCC itself. GCC cannot work without libgcc for many targets at least. Yeah.
But kernel doesn't use libgcc in implements.
I know. So I added that back.
Let me describe a use case for you, just so you. I mean, where we're. One use case is that we have a user space that consists of one directory, the root directory, and one file, init. That's all.
Right.
And then we build the init with nolibc so that it is very tiny because it gets replicated across in certain build things.
But libgcc just becomes part of your binaries for the code you run. So part of the kernel or whatever.
If the compiler puts it there, it's there.
Yeah.
Yeah. Anyway, what was their case is that sometimes the modulo and division routines were missing, but these are easy enough to re-implement.
The thing it says here, may have to re-implement libgcc stuff. Many Linux architectures re-implement lots of libgcc, and often incorrectly. And you can't just put some extra command line argument, and then it gets the actual libgcc. And that just works. So, yeah.
Can we keep going for another 15 minutes? Because that's when the lunch starts, I think.
It's at 12:30, but technically this ends at 12:15.
Okay, can we have the recording until lunch? Okay, so then we can finish this and then we can do the verification.
Okay, so number of people appreciate the possibility to contribute via DCO instead of FSF copyright assignment, and that compared to several years ago, the Linux kernel build or execution doesn't randomly break when you upgrade GCC versions. So that seems much more stable now, I guess also because of improving the Linux kernel use of C right, and hearing about GCC Rust progress, some questions there, some of them already got discussed earlier, and we will have a Rust presentation on another day. Okay, so that was again, I mentioned the Rust CodeGen GCC project, which is in upstream Rust by now, but I think needs to be enabled with special flags. and the GCC RS, the proper front end in GCC itself, which currently has the goal to get usable for the Linux kernel Rust crate. Right, yeah, not going into the details. Then we had this GCC BPF thing where I couldn't really provide an update, but right. But the interesting thing was we had this Google Summer of Code project, Piyush Rai working on tooling for running GCC BPF tests on a live kernel, mentored by people who are in the room here. And I did a live demo of that, and Jose asked me to do that again here. We use, sorry. Can you see that? Yeah, that looks good. So this system here, Debian testing system, as of recently, has Linux 6.12 kernel, and we would like to test the GCC generated BPF code that the kernel verifier in particular accepts this, and test this across several versions of Linux kernel, and with that several versions of the verifier. And so there is a VM test program from external that is some interfacing between a Linux kernel image and QEMU. And you can use that, you specifying a rootfs, which just the system here, and then run commands in that virtual machine. So we can, for example, use that to run a 6.14 kernel. The tool actually builds the kernel itself with BPF configured, and then caches that, so that's why it's reasonably quick here. So you see we have now run the uname command in this virtual machine, and then we can use the same for running check GCC with this target board, some interfacing, the BPF torture test suite with this kernel version. And currently that is just 2 test cases, which are running with several optimization levels, because that affects code generation, obviously. The first one is an invalid memory access. I will show the source code in a second. These fail to verify, that's why we get the X-fail for execution test. And another case is a valid use of BPF infrastructure, and we get that loaded, and the verifier prints that it accepts.
Well, expected fail.
Yes, that's not quite the right thing here, but can.
Well, I know.
Yeah. Can fix that up. I didn't do that.
It's too late.
Yeah. So that's the invalid memory access. You declare an int array of 4 things, and then access the 5th, which of course in C compiles because C. But we can see in the log file here, one example, the invalid memory access that GCC compiled up here, and here we invoke this VM test interfacing, and then get the log BPF program failed to load. So the kernel verifier correctly rejected this, and some log of what is going on. The other thing was the trace open at, which looks like this. So that's a small snippet of C code compiled to BPF, which I don't actually know what it does, but it looks like attaching something to the open at when we enter that function, and then would execute some code there. And we expect that the verifier is able to prove that this is stuff that may actually execute in kernel land. And we get the passes here and some more. So here again, we compiled it, then we use this tool to load it onto the kernel and get the message program successfully loaded. So that's what this project wanted to achieve. So the student passed Google Summer of Code. Now we of course have to integrate that in GCC and extend it and make it more performant and all that, but a good first step, definitely.
So now we can have a dedicated test suite in GCC with a free key to validate code. So we will know if there is some change in some optimization paths or something that makes GCC to generate not verifiable code. Hopefully, we should be able to catch regressions.
That's good.
Hmm.
What's the mechanics of it? Do you launch a queue at a time?
Currently, yes. And that has quite some overhead, as you saw here.
So how long does 12 tests run? Roughly.
So here you see when it pauses, that's invoking QEMU and loading the kernel image. And so we can parallelize that, of course, that's just a serial thing. But yeah, we should improve that in some way too.
And we could get it run in the CI.
Stripped down image that boots there? Like
That's something I don't know, yeah. Yeah, maybe that's an idea I had that maybe we could. I think it takes the config file of the host system and just enables BPF, but you don't need all the tons of.
One thing I've done with a quick hack to arrange to pass different target arguments with slightly modified SSHs in them is you can literally start up a couple of dozen QEMUs and run them in parallel.
Yes.
And then invoke all the tests in parallel, and it gets as fast as you like, as long as you've got enough memory to run all the QEMUs.
The only tricky thing with reusing an image is that, you know, if you find a verified bug and it does crash the kernel, but I don't know how often that is. So
With GCC it happens sometimes. The verifier seems to be very Clang, too used to Clang, let's say.
Love-hate relationship.
No.
All right.
Not the fault of GCC, eh?
If I may, I have two entirely unrelated topics I wanted to cover while people are in the room. Firstly, so I'm Dave Malcolm, I work on GCC, and I'm the maintainer of libgcc JIT, which is horribly misnamed because it's the ahead-of-time code compilation thing that is used by, in particular, by Rust-C CodeGen GCC. And I basically was wondering if Antonio or any of the other contributors to Rust-C CodeGen GCC are present, and if they need anything from me. In order to make that Rust option better. And I'm not seeing any hands or people saying hi. So the other is, you had a talk, Jose, you were asking about the static analyzer.
Yes, because there was a Baxilla which is...
Yeah, okay. So I'm also the maintainer of, and this is more what I'm doing these days, is the GCC static analyzer. And a couple of years ago, I put in some hooks that specially designed for tracking that, basically teaching the analyzer about the user space, kernel space boundary, so it can focus its attention on info leaks and unsanitized, like ioctl calls. I don't have the cycles to track kernel development, but what I'm saying is if there is a kernel developer who would want to sort of pair program with me virtually on making that work on I have it working for old kernels, but the syscall interface has changed enough that it's non-trivial for me to fix. But yeah, I would love a fellow contributor to so that we could basically automatically detect bad ioctls in the kernel code.
I don't think anyone here has. I don't think anyone here has the bandwidth right now. But that said, I may know people. So maybe send me your contact, and I mean, like Case Cook, who's he's the security guy for like maintainer of the kernel. Basically, he has people that he works with that he could assign if this is something that he thinks is useful for security point of view. That might be something I could help you with, maybe. Okay.
All right, so the BTF deduplication stuff, we can do it the first thing in the BPF in the afternoon, after lunch. It's after lunch, yes. And I'm sorry, I mean, this could have been better organized, and that's a suggestion for the kernel people. The same way that we do toolchain tracks in Plumbers, and we go there and organize them properly, then it would be nice if maybe we would have to talk with the organizing committee and everything, but in future cauldrons, you get some kernel people to come here to do some properly organized kernel buffer track or whatever, not this mess.
Jose, are you telling me we're being upgraded from a BOF to a track?
Well, if I continue doing it, no, because it's a mess. But if you could actually get someone here to do that, I don't know, could be. So thank you, everyone, for coming. Yeah.
Thank you.